Okay, let's talk about surfaces. There's really not, I mean, we're going to keep talking about surfaces for about half the course. Either we're talking about, for the most part, either we're talking about curves, or we're talking about surfaces, or we're talking about the interplay between the two. And okay, sometimes we talk about volumes too, but anyway, surfaces are really, for us, we're almost always going to think about surfaces inside R3. So in three-dimensional space, there are really three ways to think about a surface, typically. The one is the graph. So you could look at z is equal to f of xy. Right? You could look at the level surface. Level surface would be something like f of xyz equal to some constant. So really, the level surface says the solution set of an equation is describing the surface. And then the parametrized surface is, again, going to give you a pair of parameters. And we've already seen these ideas for, the plane, right? We can describe the plane either by its normal equation or by parameterization. Same is true for a general surface. So you need three functions of u and v. X of u, v, y of u, v, z of u, v. Now u and v are just a choice. You could just as well choose s comma t. But, so like r of u comma v is a particular point on the surface. And I usually give the surface a name like, I don't know, s. So that's it. I mean, we've got these three viewpoints. I have a laundry list of cool examples in the notes. Let me do just one here right quick. Z equal to x squared plus y squared. All right. This is what's called a paraboloid. Like, basically it looks like this. All right, so that's its graph. Level surface, you can take the graph and make it into a level surface. It's very silly, but here it is. X squared plus y squared minus z equals to 0. There's your level function. So there's an obvious and kind of almost stupid way to get between the graphical view and the level surface view. You can't always make something a graph, but you can almost always make something a level surface. You can't always make something a graph because you may or may not be able to solve for z to describe the thing, you know? Parametrized surface, natural choice of parameters here. There are various ones. You could actually, this is called the Monge patch. You just use x and y as your parameters. That's one choice. So you just put in the formula for the z component. That's one choice. I'll call that one. Another thing you could do to parameterize this surface is you could use, like, I think you could use theta and z in the following sense. Let's see here. Square root of z, cosine theta, square root of z, sine theta, and z. See, that you say, well, what? That's weird. That's weird. Why do you do that? Well, check it out. If this is x and this is y, if we take x squared plus y squared, what do we get? We get square root of z squared times cosine squared theta plus sine squared theta, which is just z again if we insist that z is non-negative. So when we plug the parameterization into the equation describing the paraboloid, it works. So it's the same idea for finding a parameterization of a surface. These are the three viewpoints. So we'll talk more about those as we go on, of course. Let me show you my examples. So here's the graph of z equals x e to the minus x squared minus y squared. That's kind of a funny one, isn't it? Here's the graph z equals to cosh of xy. That's a really quite something, actually. I think I have a definition for a parametrized surface in n dimensions here. Okay, so there you go. Here's a picture of a portion of a sphere. There's a parameterization for a portion of a sphere. So I'm actually sharing with you in these notes some useful formulas for later homework problems, because later you might be faced with the problem of parametrizing a sphere or a cylinder or something. And I show how to do all of those things in this section. Like, here's how to parameterize half of a cylinder that opens vertically. Here's how to parameterize half of a circle that's kind of like horizontal, like that. Cylinder, rather. Here's something called a hyperboloid of two sheets, and here's a parameterization of that piece, and there's a parameterization of that piece. Here's a hyperboloid of one sheet, and I've got a parameterization of that. So here's some, important level surfaces. Of course, the plane. Here I got a stack of planes. This is a trefoil, I think. There you go. It's kind of like some kind of pipe connector or something. Of course, the sphere is a level set. If you look at x squared plus y squared minus z squared equal to a constant, and then you vary that constant, you can see that you go between different cases. You go between hyperboloids of two sheets, the cone when you get to 0 there, and then hyperboloids of one sheet. So these are, hyperboloids and cones are related. Same level function, different values given these different cases. There's an ellipsoid, there's elliptic paraboloids, there's hyperbolic paraboloids, there's elliptic cones, there's hyperboloids of one sheet, as I talked about. And I give the standard formulas for all these guys in here, right? Hyperboloids of two sheets. And now, of course, if you have a graphical, I'm not sure what you guys have in terms of computers and visualizing three-dimensional things on the computer. We don't necessarily need it. It's nice to have it if you do. If you don't, there are techniques of how to graph things by hand. Pretty much what I describe in here is to graph a surface by hand. Focus your attention on some two-dimensional slice and then kind of put it together. These are called forming traces of the surface. So here I have traces of the ellipsoid along the xz, the yz, the xy plane. And so an ellipsoid has ellipses as its traces. And here I kind of explain how I think about carefully graphing a cone. And then I have some combined, these are combining the concept of surface and curve to make some word problems, like find the curve of intersection for this and that. And so I put the equations together and find a parameterization for that intersection curve. Oh, here's a problem that involves Madara and Jack Bauer. So that must mean that I wrote these notes when 24 was still on, and I was reading the manga, probably, of Naruto. So yeah, surfaces. We will do more with surfaces. That's, in a nutshell, kind of like all you need to know at the moment. You need to be aware that there's this laundry list of standard examples, and I will keep talking about those. If you don't already know them, that's okay. We'll try to continue the education. Terminology for the hyperboloid, the paraboloid, the sphere, the ellipsoid, those things. We'll try to keep using those words as we go on, and eventually we'll get used to them. Hopefully you're already used to what a plane is. So anyway, I'll shut up there, and we'll pick up next. I think next is the coordinate systems. So thanks.